our next section, power series. So the general term is sigma n from 0 to infinity. A sub n here could be your expression, and then x is your variable, c is the constant. So parenthesis x minus c to some n. And if you expand it, if n start from 0, you're going to have a sub 0, anything to 0 equal to 1, a sub 1, x minus c to the first power, and so on. So this is the general term of power series. So basically you're going to have some expression, some x minus some constant to some power. And c here is the center, it's a constant. Now let's look at our example. They want us to state where the power series is center. So at this point we're just going to look at the center. So the first one, you see all of this. This is just some expression here. And if you write this, you can write it as x minus 0 to the n. So your center would be 0 in this case. Your c, which is the center, would be 0. The second one, you have this series. Again, x minus 2, everything to the n. So your c here is 2. So your center is at 2. So now we're just going to concentrate on the center, right? We go to some more detail later. And this one we have alternate sequence series. So x minus pi to some power. So c here is the pi, so center at pi. Alright, now you know how to find the center of the power series. Now let's look at the first example. Find the radius of convergence of the power series. We have a power series here, right? First of all, we have to find a way to show that it converges. After that, we have to find the radius of it. The radius of it could be 0, could be infinity, or some number. So from this one, I choose to do the ratio test. It's not going to always be ratio test. As you recall, ratio test that if we can show that is less than 0, less than 1 is converges, greater than 1 is diverges, equal to 1 is inconclusive. So I choose to do the ratio test for this one. So this is 3x to the n would be my a sub n. So my a sub n plus 1 would be 3x. Instead of n, I have n plus 1. And then I take a limit as n go to infinity. Now 3x to the n plus 1, I can rewrite it as 3x to the n times 3x. They have the same base. So basically it's just power 1 here, so n plus 1. The reason I do that so that I can reduce the numerator and denominator. Now I end up as limit n go to infinity 3x, which is equal to absolute value of 3x. I take out the 3. Now to make this converges, I have to, it has to be less than 1. So I take out the 3, absolute value of x less than 1. I divide both sides by 3. So absolute value of x is less than 1/3, which means x is between negative 1/3 and 1/3. And if you rewrite this as x minus c, your c would be 0. So the radius will be 1/3. And the interval of convergence will be between negative 1/3 to 1/3, and the center is at 0. Alright, let's look at more example. Hi everyone, let's look at more example. I just want to show you different technique and different tests that we can apply. Alright, look at this example. I have sigma n equal to 0 to infinity 2x quantity to the n. Let's say I decide to use geometric series. So this is geometric, so you have sigma n from 0 to infinity, a, r to the n. And to be convergence, your absolute value of r has to be between 0 and 1, strictly greater than 0 and less than 1. So let me rewrite this. I rewrite this way. So my a is 1, my r is 2x. So I want to see the convergence interval. So I set it less than 1 because if it's less than 1, it's converges. Then I factor out the 2, divide by 2. So if you rewrite this, you can write it as x minus 0 less than a half, which means the center is at 0 and radius is a half. So if 0 is here, you go to the left, it's negative 1/2. Go to the right, it's 1/2. So the convergence interval is negative 1/2 to 1/2, not including the endpoint. All right. So let's look at the next example. I have the series here, and I decide to use ratio test. All right. So this is the ratio test, and to be convergence, it has to less than 1. So I replace all the n by n plus 1. Now instead of divide, I reciprocal the second term right away. So just to save some space. So then I have this multiplication of this. So the numerator here is x to the 2x plus 2. I can rewrite it as x to the 2x times x squared because I want to cancel with the denominator here. And this one, I multiply the 2n, so I end up 2n. I multiply the 2 in, then I have 2n plus 2. And let's see, what did I do? Oh, I reduced it. Okay. So this one is going to be 2n. Okay, the 2n will cancel out basically. All right, so I'm going to have 2n plus 2, 2n plus 1, and 2n factorial, and then it will cancel with this one. I skip step. You see that, I hope. So this one I can write it as 2n plus 2, 2n plus 1, 2n factorial, and cancel with this one. I confused myself a little bit. Now, this is what you have left. All right, this is what you have left. Now, this part, think about this. As n go to infinity, doesn't matter what x is. X can be any number at all. This whole thing will equal to 0. Regardless of what x is, as n go to infinity, this whole thing will be 0. So 0 is less than 1. So the series converges for all x. So if it converges for all x, the radius must be infinity. Alright, so let's look at the next one. This is my series. Again, my famous one, I guess, ratio test. So I have to rewrite this. So this is n plus 1, n plus 1, n plus 1, and this is my first term here. I just reciprocal it. I distribute the 2 in right here. Alright. The next step, I expand it so I can cancel it. So I expand this one to 2n plus 2, 2n plus 1, and 2n. So I can reduce this to right here. And then n plus 1, I write it as n plus 1 times n factorial. So I can cancel it with this one. Alright. X to the 2n, I cancel. So after cancel all that, simplify all that, I left with this. So again, I want it to be less than 1. As n go to infinity, the only way you can make it less than 1 is at one point, which is at point at x equal to 0. Because if x equal to 0, the numerator will be 0, right? And then n go to infinity, and then you're gonna end up 0. So the only point that is less than 1, which is 0 here, x equal to 0. So there is no radius, which means radius is equal to 0. Alright, let's see more example. Alright, let's look at our last example. I have this alternate series here, and when you have negative 1 to the n, it's gonna alternate negative 1 and 1 and so on. Again, I choose to do the ratio test. So this is the ratio test, so all my n, I'm going to put n plus 1. So this is my first term, divide by this term right here. So I reciprocal it to make it multiplication. And then I expanded negative 1 to n plus 1 is the same thing as negative 1 to the n times negative 1 to the 1. That's the same thing. Same as here, I expanded. Same as here, 2 to the n plus 1, I write as 2 to the n times 2 to the 1. And then I start to reduce it. So this is what I have left, x plus 1. This 1, because it's inside absolute value, is going to be 1. So we're just not going to worry about that. And this is 2. And limit as n go to infinity of this, it's just that, right? So I want it to be converges. To be a convergence, it has to be less than 1. What I did is I take out the 1/2. I take out the 1/2. The reason I take out the 1/2 because I want to have this by itself. So I multiply by 2. Now this is in the right form. So this is my x. So my c is going to be x minus 1. So my c is going to be negative 1, which means the center is at negative 1 and the radius is 2. Now if you graph it, negative 1 is here, radius is 2. Go to the left 2, go to the right 2, you're going to have negative 3 and 1. That is the convergence of the interval negative 3 and 1. Not including negative 3 because we want to be strictly less than 1. Not including 1, same reason. Right? So we finished chapter 9.8. I see you next time. Bye.